We've previously seen that vectors are quantities that have both a magnitude and a direction, and they can be represented as arrows. What we're going to focus on now is some of the things that we can do with vectors. Things like adding vectors, subtracting vectors, multiplying vectors. And in each case, I want to physically motivate it to show you how this is going to arise in your physics class. So the first operation that we're going to consider is sliding a vector. Suppose I have a vector. Here it is. And now suppose I slide it and move it to this new spot on this page. As long as I simply slid it, but I didn't rotate it, and I didn't grow it or shrink it, I didn't change its size, it represents the same vector. Where does this come up? So let's say, for example, I have an object and there's a force on it. Let's say a 10 Newton force pushing upwards on the object. And I want to represent that. So I go and I draw a vector pointing up of strength 10 newtons. So here's my force vector. Now, if I wanted to, instead of drawing the force vector here, I could have drawn it over here. Or I could have drawn it on a different spot on the page, over here, or maybe over there. Regardless of where I happen to draw it on the page, it still represents a force that's pointing upwards of magnitude 10 newtons. So it's still the same vector. So whenever you have a vector, you can freely slide it over as long as you don't tilt it and as long as you don't change its size. It's the same vector. One common place where this comes up is as follows. Suppose I have an object, this blue particle here, and let's say there's a rightward force acting on that object of size F. So here's the force acting on the object. So I drew it like that. If I wanted to, I could have instead drawn the force pointing like this. I just slid it over from here to here. Okay? So it's still the same force. It's still a force of size F pointing to the right. Doesn't matter if I drew it here or if I drew it here. I'm allowed to slide vectors around. Now it may look a little different to you. It may look like, hey, in this case I'm pushing on the particle, whereas in this case I'm pulling on the particle. But it makes no difference. The particle is going to behave in exactly the same way. Okay? So that's the first thing that we can do with vectors. You can slide them around. Another thing that you can do with vectors is you can multiply them by a scalar. And you'll remember that a scalar is just an ordinary number. It doesn't have a direction, it's just a number. So for example, here's a vector, and I've given it a name. I've called it A. Now let's say I multiply this vector by the number 2. 2A. That is simply a vector that points in the same direction as the original one, but it's just twice as large. That's how you multiply vectors, by a scalar. Let me show you where this comes up in practice. Suppose, for example, I'm looking at a particle that's moving along and it's traveling at a certain speed in a certain direction. So I can represent its initial velocity by a vector, let me call it v. Now suppose that at a later time the particle's moving in the same direction but twice as fast as it had been before. In this case, I would denote its new velocity as twice the old velocity. By the way, you can also multiply a vector not only by 2 or 3 or 16, but any number, including negative numbers. So I can take a vector, let's call it A, and multiply it by -3, for example. And what do you think that might look like? Well, if I multiplied a vector by +3, that would be the same vector pointing in the same direction as the original, just 3 times longer, 3 times the magnitude. But the minus sign tells you that the direction of the arrow of the vector is flipped. So in other words, if I have a vector and I multiply it by -1, all I'm doing is flipping the direction of that vector, flipping the arrow. But there's more that we can do with vectors. We can add vectors together. And this is a very important thing that you're going to encounter a lot. So here are two vectors. Here's a vector that I called vector A. Here's another vector that I called vector B. Suppose I want to add them together. Here's what I do. I'm going to slide the two vectors around until they're pointing head to tail. So in other words, the head or the tip of this arrow is up against the tail end of this arrow. Remember that you're allowed to slide vectors around. It doesn't change them as long as you don't rotate the vectors or stretch them or shrink them as you're sliding them. So here I've just taken those two vectors and slid them around so that the head of one is against the tail of the other. Now, to add these two vectors together, I draw an arrow starting at the tail end of the first vector pointing to the head of the second vector. So this dashed red arrow that I drew, that I labeled vector C, represents the sum of vector A plus vector B. So vector A plus vector B gives me vector C. That's how you add two vectors together. Now, where does this come up in practice? Let me give you a number of examples. Sometimes we'll want to add displacement vectors together. So for example, suppose you walk 10 meters in a northeasterly direction. So you start here and you walk 10 meters to here. So that's your displacement, 10 meters in that direction. And then once you get here, you walk an additional 6 meters in the north direction. Okay? So you're walking from here to here. Where are you in relation to your starting point? Well, to get that, I'll add this vector with this one. Notice that they're and I simply draw this arrow, and this red arrow represents the sum of these two displacement vectors. So you can think of it as follows. If I walk from here to here, and then I walk from here to here, that's equivalent. I end up at the same spot as if I walked from here to here. So this red arrow represents the sum of these two vectors. Let me give you another example. Adding force vectors. Very often in physics, you'll have an object, but there's more than one force acting on that object. And we want to know what the total force or the net force is on that object. So we want to add the individual force vectors together. So for example, let's say there's a 5 Newton force on an object pushing to the right. And at the same time, there's also a 12 Newton vertical force pushing on the object. So both of these forces are acting on the object simultaneously. So if I want to know what the total force is, or the net force, I'm going to add up these two vectors. Now remember, when we add vectors together, we have to place them head to tail. So I'm going to slide this 12 Newton force over so that it's head to tail against this other force vector. And now, this red arrow represents the sum of these two force vectors. So this new force, which is 13 newtons in size, is the total force acting on the object. By the way, we could turn this around. If you have an object and I tell you that the total force on it is 13 newtons in this direction, you can, if you want, think about that as being really a 5 Newton force to the right plus a 12 Newton force upwards. Another example, we can add velocity vectors together. So let me illustrate using a particular example. Suppose you're looking at a river and the river flows east at 4 meters a second. Okay? So here's the river and there's a current in the river flowing to the right at 4 meters a second. And you have a little rowboat, there you are, and you're able to row at a speed of 3 meters per second relative to the water. So you aim your boat directly across like this, in other words, in the north direction, and you start rowing. Now let's think about what's going to happen. If there was no current at all, and you start rowing like this. So you've got a velocity 3 meters per second in the northern direction. So you just move like that, straight up. But because there's this current flowing, as you're moving up, you're also going to be moving horizontally to the right at the same time. So to get your velocity relative to the ground, here's what you do. You're going to add up the velocity of the current plus your velocity relative to the current. And when I add up this vector plus this vector, that tells me my velocity relative to the ground. So in other words, the motion of the boat is going to look like it's moving in this direction, namely in this direction at a rate of 5 meters per second. By the way, we could turn this around. Suppose you have an object that you observe is moving at 5 meters per second in that direction. If you like, you can think of that motion as being composed of moving 4 meters per second this way simultaneously with moving 3 meters per second this way. That will give you this motion. And lastly, not only can we add vectors together, but we can also subtract vectors. So here's two vectors labeled A and B, and suppose I want to subtract them. Here's how we do that. We place the two vectors tail to tail. So I slide the vectors around till their tails are touching. And suppose I want to form the vector A minus B. That's what I want to compute, A minus B. So I draw an arrow from B towards A, as shown here. And this red dashed arrow, which I've labeled C, represents the vector A minus B. That's how we define the subtraction of two vectors. Now, where does this arise in practice? Okay. Well, in physics, you'll often find that vectors can change in time. So suppose, for example, I have a vector that's originally pointing like this. I labeled it A initial. That's what the vector looks like at the beginning. But then later on, let's say the vector now looks like this. This is what it looks like at a later time. I call that A final. So the vector has clearly changed. And if I want to know by how much has this vector changed, I'm going to subtract these vectors. I'm going to take A final minus A initial. So I do that by placing the two vectors tail to tail. That's already done. And then I draw an arrow from the initial towards the final. And that red arrow represents the final vector minus the initial vector. It tells me by how much the vector has changed by. By the way, I gave this red vector a name. I called it delta A. In physics, the symbol delta is often used to denote a change. So this tells me the change in the vector A. It's simply the final vector minus the initial vector. Let me give you another example of where this arises when we're going to subtract vectors. Okay? Often we're going to be monitoring the motion of a particular particle. So you see that red particle there? Imagine it's been traveling along this path shown here. So there it is traveling along that path. And at a given instant in time, there it is. So I draw this arrow, I call it a position vector, pointing to where the particle currently is. I give this arrow a name, I call it position vector R. And I made it as a function of time because this vector can change. As the particle moves, its position is changing. So suppose, for example, the particle starts off here and moves along this red path to here. Okay. So here's the initial vector, what it looked like at, let me call it T initial, and here's its position at a later time, let me call it T final. So if I want to know what's the net change in its position, or in other words, what's the displacement of the particle? The displacement represents the net change in the particle's position. I just subtract the two vectors. I take the final vector minus the initial, and that's this red vector. I called it delta r because remember delta denotes change, so delta r represents the change in the particle's position. And it's simply its final position minus its initial position. So that's another example of where we are going to find cause to subtract vectors. By the way, one final remark here. When you subtract one vector from another, so for example, if I do vector a minus b, that's the same thing as adding the negative of a vector. In other words, a plus negative b is the same as a minus b. So let me illustrate that for you. Suppose I want to take a minus b. So here's vector a, here's vector b. So when we subtract two vectors, we put them tail to tail, and then we draw an arrow from the one that we're subtracting off towards the first one. Okay? And there we have it. Vector c is a minus b. But equivalently, I could have said, well, let me add a plus negative b. That's the same thing as a minus b. But let's draw this out. So here's vector a, just as before. Here's vector negative b. So if vector b is pointing up, vector negative b, I just reverse the arrow. It's pointing down. So now what I'm going to do is I'm going to add vector a to the vector negative b. And remember, when you add two vectors together, you place them head to tail. So I slide these two vectors around to the head of one is against the tail of the other. So here's a plus negative b. And that red arrow, which I labeled c, is the sum of vectors a plus negative b. And notice that this vector c is exactly the same one as this vector c. It's got the same size, and it's pointing in the same direction. It's drawn on different spots on the page, but that's okay. It represents the same vector. So a plus minus b is the same as a plus negative b. Okay, so we finished with this section of the tutorial. So what I want you to do is grab a piece of paper, a pencil, and a calculator, and go to the section labeled Practice Exercises associated with this tutorial and give it a try. And after you've given it a fair try, then you can look at the solutions that are provided to you. Good luck.